Hi Geometry, this is Unit 2, Lesson 9, page 252, and today we're going to be looking at a proof of the side-side-side triangle congruence theorem. We've already been using that in some of our problems. So Pyra was given this task to complete, to use a sequence of rigid motions to take STU onto GHJ. She already knew that ST and GH were congruent. She already knew that TU was congruent to HJ and SU is congruent to GJ. And you'll notice that I marked those in the picture with a single, double, and triple tick marks. So she probably set out doing this like you and I did in the last Unit 1. She probably translated over one vertex to one vertex, and then she rotated around that vertex until another vertex lined up. And then finally, Pyra reflected it over so that one triangle lined up on top of the other triangle, and that's how she knew that the three sides were definitely congruent. This is a proof of why that works out. These statements that you see here are statements from our sentence frames page, but the statements are already on the page. We don't have to look for them. All we have to do is fill in our blanks from this particular example. So first of all, when I first translate this over and rotate, my triangle is sitting on top of my old triangle. So I'm going to lightly sketch it so I don't have to keep sliding my patty paper. And so when I first move it over, U prime, T prime, and S prime. So when I first translate it and rotate it, it's setting on top of the other triangle in such a way. So let's take a look at statement number 1. It says ST is the same length as blank, so they're congruent. Well, I already knew that ST was the same length as GH. So let's write that in here. And so I knew there was a rigid motion, or in this case, two, a translation and a rotation that would take my ST over to my GH, which is what I've drawn up here. I took my ST over to my GH. So I applied this rigid motion, and the image of T will coincide with, and I can see it coincides with H. It's sitting right on top of H. And the image of S coincides with, and I can see it went to G. Okay, we cannot be sure that U, which we'll call U prime, that's what I called it up here in our picture, coincides with J yet. And in fact, I can see that it doesn't. So this is a problem where I still have to do a reflection. So let's talk about why that reflection might work. HJ is congruent to, so HJ is congruent to this TU. Because rigid motions preserve distance. In other words, it's not going to change its size once I translate, rotate, and I'm getting ready to reflect. Therefore, H is equal distance from U prime. H is equal distance from U prime and also J. I've already marked these with single tick marks from my patty paper and on my page. And so I know that H is equal distance to U prime as it is to J. I can see that mark in my picture. I also know that in the next statement, G is equal distance to U prime as it is to J. So I know that it's the same distance to each one of those points. So this brings me to something we haven't worked with in a while. It brings me to our perpendicular bisector. So if I could slide my book so I could use the picture on the bottom, this is very similar to the picture I had at the top. Let me just mark my tick marks that I had at the top so that it matches. So if this distance is the same, and if this distance is the same on both sides, then I happen to know that GH is the perpendicular bisector of a segment that connects my U prime and my J. I happen to notice that if it's equal distant to both endpoints, then this would be the perpendicular bisector of this penciled segment I just drew in, perpendicular bisector. Because the perpendicular bisector, if you remember, is determined by 2 points that are both equal distance from the endpoints of a segment. So I can see that my distances were equal here, and also here and here. So it says to reflect across the perpendicular bisector, Well, that's my GH. That's what I would have done anyways. I've been doing that this whole time. Once I get my triangle here, I reflect it over and it lines up perfectly. So I'm going to reflect over and it's going to take my U prime onto my J and they will finally be lined up. So therefore, after doing the reflection, all three pair of vertices coincide and I know my first triangle, my second triangle, GHJ, and my first triangle, STU, I know that they line up and they're on top of each other and therefore they are congruent. So I'm not super concerned about this page other than this is the side, side, side triangle congruence theorem. We're going to use SSS a lot in our upcoming work, and we now know that it works every time with every triangle because we've just proven it on this page. So let's change course here and do a different problem. Let's actually do our first two-column proof. This is going to be very similar to an activity we already did in class about a parallelogram. In fact, all the things I do with you in the beginning are going to parallel what we've already looked at in class, but we're going to write it up in a formal two-column proof style. So let's take a look at our problem. Let's feel like deja vu for a little bit. Quadrilateral ABCD is a parallelogram. By definition, that means that the segment AB is parallel to CD and BC is parallel to AD. So can you draw my parallelogram? Pencil it in. Go ahead and draw the transversal AC down through the middle. And in a proof, I always have something I'm given, and I always have something I'm trying to prove. In this one, I'm given that ABCD is, and I'm going to abbreviate parallelogram by using parallel symbol and then ogram. So this is what I'm given, this is what I'm told, and I'm supposed to prove that angle B is congruent to angle D. That's what I want to end up with when I'm all done. So let's for a minute talk about everything we're going to be writing up. So all the stuff we already know. So I want to take you back so you don't have to flip. I'll go back to our lesson 7. This was on page 236. And this is when we first started talking about this exact same problem. And we started to learn how to mark up our parallelogram with all these good things that we knew. And we determined all these things that I could find in this parallelogram. I determined why my two triangles were congruent. And then I determined that, for example, what I want to prove here, angle D is congruent to angle B by CPCTC. So I'm going to use all these thoughts from page 236 in lesson 7 here today in this lesson. So let's start by marking up what it means to be parallel. So I know the top is parallel to the bottom because that's the definition of a parallelogram. And I know my side is parallel to my side. Again, that was definition of a parallelogram. So let's start putting that in my proof form. So in a proof, I always have statements. You can ignore the writing in the middle of your page. And I have reasons. So first of all, in this problem, my very first statement is that ABCD is a parallelogram. The first one's easy. You're always going to write what you're given. You don't have to think at all. Just write down what you're given. So then my next statement is that my opposite sides are parallel. That's the definition of a parallelogram. That's the next thing I marked. So AB is parallel to, now be careful, this is one of those twist problems. If I put my patty paper on here, I could see that this would twist under. So AB is technically parallel to CD because my A goes to C. So I'm going to write it that way. And then also my sides, so BC, but now that I wrote BC this way, I want to write DA because B is going to twist down to D and C is going to twist up to A. So this would be DA. And I know that based on the definition of a parallelogram that we learned in Unit 2, Lesson 1. So now, how did that help me? Well, in lesson 7, we learned to look at this as like a zigzag. If my top line and my bottom line are parallel, and my red line is my transversal, then that gives me a set of alternate interior angles that are congruent, because alternate interior angles are congruent. So I know, careful how you write it, so I know angle BAC, and since I wrote it BAC, I've got to write this one as DCA to put my corresponding parts, DCA. If you're having trouble with that, go ahead and trace this on your patty paper and then go ahead and turn it around this midpoint. You'll see that this angle comes down here to this one right here. And that's because my alternate interior angles are congruent. Lots of abbreviations there, but as I've mentioned before, sometimes we get tired of writing all those things. So now I have my sides. My sides are parallel, and this is my transversal, and it gives me the other set of alternate interior angles. That's this little blue guy and this little blue guy. So let's write that here. So I can name my first angle any way I want, and I need to slide my book up so that I can. Hi, I'm back. I tore my page out and bent it so that you could see the picture and what I'm writing all on the same screen. So let's continue with my blue angles. I can name this angle any way I want. CAD, DAC, either one's fine. I'll say DAC. But once I do that, I can only name the second one a certain way. So DAC, my corresponding parts would be BCA. BCA. Again, if you're really struggling with that, trace this onto the patty paper and then rotate around your middle, and you'll see what vertices are corresponding and line up. So then that's also marked because I know that alternate interior angles are congruent. And usually here in class, I would have a student say, well, can we write them together on the same statement and use that as a reason only once? For sure. It's just, this is the first time we've done a proof, so I wanted to kind of do each step sequentially so you could see it. So then lastly, what I'm trying to do is get this top triangle and this bottom left triangle congruent. So I also know that this shared side is congruent in both of them. So that green side, side AC, is congruent to, now be careful, don't write AC congruent to AC because that's not how it goes. This is a twist. This problem twists. So AC is really congruent to CA, and that's by the reflexive property. It's a shared side. It's in both of them, so I know it's a congruent side. This is now where I know that my top triangle and my bottom triangle are congruent to each other by angle, side, angle, congruent to the other angle, side, angle. This is my included side, so it's ASA. So I now know my two triangles are congruent. You can write them in any order you want the first time. So I'm just going to write ABC. Done. So ABC. But now I've got to be careful. And now I've got to write the next triangle in the exact same order. So A goes to C, B goes to D, and C goes to A. So I have to be careful how I write the second one. And that was by the angle, side, angle, triangle congruence theorem. And now that I've done that, I know all 6 parts. I mean, I can visually see 3, 2 of the angles and 1 of the sides. But I now know the other 2 pairs of corresponding sides and my other pair of corresponding angles are congruent, which is what I'm trying to prove. So this is now where I can write what I'm trying to prove. I can write, my last statement is always my proof. This is always what you're going to end up writing last. And so I'm going to write angle B is congruent to angle D, and that reason is CPCTC. Basically, any corresponding part of my congruent triangle from the line above are congruent. So this is our very first 2-column proof, and it was long. So usually the ones you begin with are only 3 or 4 lines. So this one was a big one. If you understood it, that's fantastic. And if you had trouble with it, we're going to be doing more proofs in the next class that are actually shorter than this one. So you can always come back to this one after that lesson, and I think the flow might make a little more sense to you. So before I let you go, I want to give you a few hints on your practice. If you could look at page 256. First of all, it's a little confusing what they say here. So a kite is a quadrilateral which have two sides next to each other that are congruent, and the other two sides are also congruent. It's not a rhombus. In a kite, your congruent sides are touching. So that's what makes it a shape that we call a kite. And then it says, given this kite, show at least one of the diagonals that decomposes it into two congruent triangles. Okay, so this case, the way they use the word diagonal, a diagonal connects any two non-consecutive vertices. So non-consecutive means not one after the other, not touching. Maybe the word every other makes more sense to you. So a diagonal connects two non-consecutive vertices. So in this picture, there's really two diagonals. XZ is a diagonal and WY is a diagonal. There's two diagonals in that picture, although they're not traditionally what you think of as diagonal. So now that I've done that, which diagonal is the one that decomposes this kite into two congruent triangles? So you don't want both of these. You want the one that divides it into two congruent triangles. So that's all you. Let's take a look at number 2. Maya has proven these two triangles congruent using the side-side-side triangle congruence theorem. Okay, so side-side-side triangle congruence theorem. I know WY is reflexive, so these two triangles are congruent to each other. And why can you now conclude that the diagonal WY, and we call it a diagonal because it connects two non-consecutive vertices, why can we say that it bisects ZWX? Why can we say it bisects the big angle on top? And why can we say it bisects ZYX? That's the big angle on the bottom. Why is WY a bisector of the top angle and the bottom angle? Think a little bit about what we did today in class, proving two triangles congruent, and then what you might know from CPCTC. Lastly, in number 3, it says WXYZ is a kite, and it says angle WXY, go to W to X to Y, has a measure of 133. And I already know these two triangles are congruent by side-side-side. So I know that this has a corresponding angle in Z. So Z should be 133 degrees as well. And then it says angle ZWX. ZWX, that's the one on top, the whole thing. The entire thing on top is 60 degrees. Well, I learned something when I did the second problem. I learned something about this angle here and this angle here that make up the large 60-degree angle. So I could write in what this angle and this angle is, and I can use that to help me find the measure of ZYW, which is actually what this problem is asking for. So ultimately, you'll have that little red angle right there is what you're going to find. And actually, there's one more I want to talk to you about. If you could flip to number 6. On this particular one, some kids last year had a lot of trouble with it. So just let me mention real quickly that you can see it states that my two triangles are isosceles. You can see the larger isosceles triangle, and you can see the smaller isosceles triangle. Remember what we know in isosceles triangles, the base angles are congruent. So for instance, when it says that DBC is 84, I know that this little angle and this little angle have to be congruent. If a triangle adds up to 180, I can figure out my two little red angles. I can figure out their measure. And if I knew their measure, coupled with the fact that BDA has a measure of 24 degrees, so BDA DA is 24. I would know something about this entire angle, the purple and the red, and I would know something about this entire angle, and that might allow me to figure something about the entire angle A. And then I could simply, what I want to find in this problem, let me get a different color, we'll get a green one. I want to find the measure of this little tiny BAC. So I want to know this little tiny green angle. So if I could figure out the entire purple angle A, then I could figure out that little green part. I hope these hints were helpful to you, and I'll see you in class.